Welcome to Ask and Learn.
So in this problem, we have a block that's being pushed into a spring by a force at an angle of 30 degrees. And we want to find the power that is generated once this block is pushed 1.5 feet. We can call that S, so 1.5 feet. We're also given the weight of the block, which is 50 pounds. Let's convert that to mass. So we divide it by 32.2 feet per second squared to get 1.55 kilograms. And we also know that when the block is being pushed, it experiences kinetic friction. So we're given the coefficient of kinetic friction as 0.2. And we're given the force, which is actually a small equation. The force is given as 40 plus S2 pounds. So this just tells us that depending on the distance, the force will increase. Okay, so since we're dealing with power, we know that to find power, we need the force being applied times the velocity of the movement. So the velocity of the block will be going to the right. And so you have velocity to the right, and we have that force at that angle 30 degrees. So since power is actually a dot product, we can expand this to force times velocity times the angle between them, cosine theta, and of course theta is just 30 degrees. So here we have the force that's given to us. We know the angle, but we don't know the velocity of the block. So because we're dealing with movement of an object, we know that there's some sort of kinetic energy going on. And since a force is being applied and the block moves a certain distance, we know that work is involved as well. So we can use the work energy theorem to find the velocity. And that's given as the initial kinetic energy plus the work done by the forces is equal to the final kinetic energy. Since the block is initially at rest, the initial kinetic energy is 0. So then this becomes the work done by the forces is equal to final kinetic energy, which is 1/2 m v2 squared, and v2 is what we're looking for. Let's call this equation 2, and the equation for power we'll call equation 1. So from our equation 2, we need to find the work being done, and we know that work is the force times distance. So let's draw a free body diagram to see the forces involved. So on the block, in the y direction we have the weight straight down, and in the opposite direction we have the normal force, and we have that force at some angle. So that means that this has components. So we have f of y straight down, and then to the right we have f of x, and friction is always in the opposite direction of movement. So since the block is moving to the right, the friction is to the left, the force of kinetic friction. And because the block is pushed into the spring is going to move it back to the left by some force. So the force through the spring is to the left. It's okay. So then the work becomes the force times the distance. And since the movement is in the x direction, we just care about the forces in that direction. So we have f of x times the distance this block travels, which we'll call S2, And S2 is also given to us, which is 1.5 feet. Okay, so then we have that force. Okay, since that force is to the right, that work is positive. So the work done by the spring is to the left, which means it's negative. And the work done by the frictional force is to the left as well, so that's negative too. So we have minus the force of the spring, which is 1/2 K S2 squared, minus the work done by the friction. So we know that the kinetic friction is given as mu K, the coefficient of kinetic friction, times the normal force, times the distance this friction travels, which is S2. So here we don't know f of x, and we don't know normal force. Well, from this little triangle, we know that cosine theta will give us that f of x divided by f. So then just solve for f of x, and we get f times cosine theta. And the normal force is in the y direction. So in the y direction, we have weight, we have the normal force, and we have f of y, the y component of that force at the angle of 30 degrees. And if we say going down is positive, so we have f of y and w in the same direction, and f of n is in the opposite direction of those two forces. So when we do the sum of the forces in the y direction, we have w, the weight, plus f of y minus the normal force, f of n, is equal to, and then since there's no movement in the y direction, acceleration is 0, so this is equal to 0. Of course, we don't know f of y, and we can use the same trig identity as f of x, so then we know that f of y will be f sine theta. So plug this in and then move fn to the right, we have fn positive is equal to f of y, which is now f sine theta plus the weight w. So just plug in what we know. So f is 40 plus, and then the S2, which we know is 1.5 squared, plus, well, times sine of theta, sine of 30 degrees, plus the weight, which is given to us, that's 50. So then the normal force, f of n, is equal to 71.13. And we can plug this back in now to our equation for work right here. So let's plug that in, and also all the other values we know. It's okay. Work is equal to that force that's given to us, 40 plus, and then 1.5 squared times cosine 30 times the S2, which is 1.5, minus the work done by the spring, 1/2, times K. K is 20 times 1.5 squared, minus the work due to friction, so 0.2 times the normal force we just found, 71.125 times 1.5. So then work is 11.05. And we can plug this back in to our equation 2 to find the velocity. So on the left we have 11.05 is equal to the 1/2 times the mass, 1.55, times v2 squared. And again, the velocity is what we're looking for. So solving for velocity, we get v2 is equal to 22.09, and that's found by multiplying 2 to both sides, divided by 1.55, and all of this square root. So v2, the velocity of the block, is 3.78 feet per second. So now that we finally have the velocity, we can find the power generated by that force. So we have finally power is equal to that force that's given, 40 plus 1.5 squared, times the velocity, 3.78, velocity of the block, times the angle between them, which is cosine 30. So then finally we get power is equal to 138.31 pounds per feet seconds.